Okay, I'll start now. Just waiting for it to start, then I'll start. Okay, there's the recording started. Okay, so these are the examples that you guys must do for your assignment. I'm scrolling slowly through it. You can stop at 2.14. So you must send it in to me. You know what? I'm gonna on Brightspace. I'm gonna make a assignment thing open, and then you submit it for me on Brightspace. Will you people do that? I'm gonna ask you to not email it to me. It will clutter my email a lot. So will you please submit it on Brightspace? Okay, I hope you've heard that. There's also some examples you can do. If you want to do some extras, you can do those that's marked in yellow. I'm going to quickly start with Chapter 3 because I'm going to run out of time because of load shedding. Attenuation. When you do attenuation, we will work in dBs, and I will just explain quickly. Power in over power out, that ratio, it's a ratio, people. It's not a fixed thing like a voltage or power in watts. It's a ratio, power in over power out. So if I take the log of that times 10, then I get my value in dBs. Alright. However, when I have the ratio, say the ratio of P in over P out is 1:10. 1 watt in, 1 watt out. Optical power is always in watts. It's usually in milliwatts or microwatts, and that is denoted by P in over P out. So if it's 1 watt in and 10 watts out, it's a tenth. So it's 0.1 equals 10 to the power this. So how you can calculate this ratio? You take the dB value, you divide it by 10, and 10 to the power of that. So if I can easily do it in my head. I don't even need a calculator. So if I have 10 dBs, if I have a dB value of 10 and I want to convert it to this ratio, I will say 10 dB divided by 10 is 1. So it's a 10 to the 1. 10 to the power 1 is still 10. Okay? So that is my ratio, therefore, is 10. P in over P out. So that means my power in was 10 watt and power out was 1 watt in this case. Does that make sense? Are there any questions? This is very important, and a lot of people can't do this one. Now in dBs, how it works, we can add gains in dBs, but we cannot add numerical ratios. This P in over P out, we cannot add that. So when we've got a lot of dB losses, like a 3 dB loss plus another 4 dB loss plus a 5 dB loss, the total loss there is 9 plus 5, which is 14 dBs. Okay, we can, when there are different dB losses over our cable, we can just add them. That's the advantage of dBs. So we want to work in dB scales. That's the reason why we work in dB scales. Because most people don't understand why do we do this funny sort of thing. It's because we can add in dBs. So you must be able to work from a ratio to the dB value. This is the ratio, and we can get the dB value of it. And this is the ratio. We can calculate the ratio by taking that dB value and dividing by 10, and 10 to the power of that division. So this formula is also important, 3.3. This is a per kilometer value. So if we have dBs per kilometer, in that case, I want the values in dB per kilometer. I will take my ratio of the fiber input over the fiber output. It can be the power of the laser input towards the power output of the photodiode at the output of the fiber. So that ratio, P in over P out. I take the log value times 10 and never times 20. I always multiply by 10. For optical power, even if it's voltages, we also use log 10 log 10. Alright, so the dB attenuation, alpha dB is the signal attenuation per unit length. So in this case, per kilometer. Here's an example. It's a nice example. If you do this, you'll understand it immediately. Do this example 3.1. When the optic power launched into an 8 kilometer length of fiber, it is 120 microwatt. The output is 3 microwatt. So it's 120 over 3. 120 over 3 is 40. So the ratio will be 40. So what I want over all attenuation, so what you do here, signal attenuation is 120 over 3, so it gives you that value 10 log 40, which is 16 dB in this case. So per kilometer, it will also be 16 dB per kilometer, like they say here, 16 dB per kilometer. Sorry, but remember it's 8 kilometer, so for the total length, over 8 kilometer, we must just divide it by 8. So dBs can be divided by the kilometer value, so that gives you 2 dB per kilometer. So in this case, they take that value and they say that alpha dB length, the dB length value is 2 times 10, and that is 20 dB, because they want it for 10 kilometer fiber. They only given you an 8 kilometer fiber, but they want it for a 10 kilometer fiber. It says here in C. They want it for a 10 kilometer fiber. That's why you must calculate and times that 2 dB by 10 to get it for 10 kilometers, then it's 20 dB. However, the link also has 9 splices at 1 kilometer intervals. Now each splice has got a loss of 1 dB. Do you guys see here? Each splice has got a loss of 1 dB. So it's 9 dB per splice. So we must add that 9 dB to the 20. That's why it's 29 dB. Right. And then if I say there is a loss of 1 dB over each kilometer as well, fiber, then there is another 9 or 10 pieces of fiber, and you must add that losses as well. That's only if I tell you there's another 1 dB per kilometer of fiber. And we also added that here, in which case we will have 39 dB. But okay, the numerical input-output ratio, you see here this word, this English word, numerical input-output ratio. You must learn that word. I will ask that word in exam. I won't give this magic number. You must know, I want this ratio. If that ratio is that value, so it's 794. The numerical input-output power ratio. Right, material absorption losses, intrinsic absorption. I'm going to talk about that. And intrinsic absorption is absolutely pure glass and very little intrinsic absorption. There's no water in it and there's no intrinsic absorption really, but it's never pure. So the impurities, and you can read this paragraph, it will tell you about those impurities and how it works and what happens. But they are always oxides, fluorides and chlorides in glass, and glass is never pure. Look, they're making the silicon glass out of sand, did you know? So it's actually sand. sand outside, and they purify it. That's why it becomes silicon, which is so pure. So it's never perfectly pure. It's 9.999% pure. Now, extrinsic absorption, which is another one. Intrinsic is inside the glass, alright? Extrinsic absorption is some metal impurities that comes from the outside, and it goes also into the glass. So there can be a lot of stuff, some chromium, copper, ferrite, in nickel, and so on, and all kinds of extrinsic absorption. It's these metals. You must remember that it's always metals. They are usually like chromium and copper, okay? That's the difference between intrinsic and extrinsic. Extrinsics are metals, and intrinsic is oxides. You have seen yellow oxides like fluorides and chlorides. Okay, they are mixed with the gases, and that's how they get in. But the metals get in because there's metal in the sand, and there's actually metal everywhere. Okay, I'm going to skip this. I'm just showing you those two words. You must know what it is and the difference between them. Then we get to linear scattering losses. This is a bit difficult, people. You must concentrate now. On the linear scattering losses, we have two types in yellow here, Rayleigh and Mie scattering. Now that's scattering inside the fiber, and it causes losses for us. And there's a formula I'll show you now, how to calculate Rayleigh scattering. First, Rayleigh scattering. What is Rayleigh scattering? I will ask you that in exam, I promise you. Rayleigh scattering is a low absorption window between ultraviolet and infrared. It results from inhomogeneities. In other words, little things that's like dust and so on. Inhomogeneous of random nature compared to the wavelength of light. So that's the definition of it. This yellow, you must just learn it. These inhomogeneous manifest themselves as fluctuations, and it's frozen in the glass lattice when they cool it. The glass is molten when they make it, but it's frozen into the glass lattice when it's cooling off. Right? And what else can I say? Rayleigh scattering is strongly reduced by operating at the longest waveframe. How can we reduce Rayleigh scattering? It says here, Rayleigh scattering is reduced by operating at the longest wavelengths. Don't operate at the shortest wavelength. It's too much there. You must operate at the longest wavelength. In other words, the highest frequency. That's how you get rid of Rayleigh. I'm not going to this example. Skip this example to 3.2. Skip it. Skip this one. Okay, Mie scattering. The first one was Rayleigh scattering. This is now Mie scattering. Mie scattering is also linear. These two are linear, okay? The ones that's non-linear is Raman and Brulin. We get to them now. But the linear ones are these two. So linear scattering also occurs to homogeneities and results from irregularities in the core cladding interface. Here it is. There's irregularity on the core cladding interface. So it's between the core and the cladding. Mie sits there. Remember that. Rayleigh don't sit there. They are inside the glass all over, but this one is on an interface. Now they can be the length and diameter changes in the fiber, also strains and bubbles. There can be an air bubble or a water bubble on the cladding interface. Okay. Homogeneities are mainly in the forward direction. So forward direction means the direction where the laser light goes. Okay. So it's always in a forward direction, not in a backward direction. Alright. Raman and Brulin are backwards, but we'll get to that. So mixed scattering can be reduced. Mixed scattering can be reduced by removing imperfections due to glass process, carefully controlled extrusion of the fiber, more careful extrusions, maybe slower and more controlled. Increasing the fiber guidance by increasing the refractive index. So you can reduce misscattering by this. See how you can reduce it. How do we reduce Rayleigh scattering? You still remember? Rayleigh scattering is reduced by operating at the longest wavelength. Do you see the difference between Rayleigh and me? You must know this theory. You must know these things. I will ask them. Non-linear scattering. Now we're talking about them. Right, non-linear is Brulin and Raman. Now, it's in a forward direction only. No in a forward, nothing in a forward. Remember me and Rayleigh was forward, okay? But this one is forward. Only backwards. Where does it say backwards? I'm trying to find the segment. Here it is. 0 in the forward, but mainly in the backward process. There it is. 0 in the forward direction. So Brulin is only backwards. Okay. The formula for Brulin. Here it is. You must know the formula also. For Brulin scattering, to calculate in watts, the Brulin scattering in watts, the losses in power in watts is 4.4. Now listen carefully, guys. This is complicated. Times 4.4 times 10 to the minus 3 times d squared. That is the diameter. But there's no units for that d. It's not in meters or millimeters. It's just a number. Okay? It's just the diameter and the operating wavelength. Okay? So there's no units to d in lambda. So d squared, if it's 10 micrometers, then it's 10 times 10, that's 100. It's not 100 times 10 to the minus 6. Don't do that. It's just 10 times 10, which is 100. It's unitless. There's no unit on d. Lambda, don't take the unit. I know it's maybe 2 micrometer or nanometer. Don't do it. Just 1.2 times 1.2. Without, it's the only formula in this book where there's no dimensions inside the formula. Okay. So it's the wavelength, and alpha is the core diameter, not the radius. Look here, core diameter. It's not the same as that other alpha we had this morning, which was the radius. This is the diameter we put in here, and there's no on the diameter also. There's no units. So if the diameter is 10 micrometer, you just say 10 times 10, which is 100. Don't say 10 times 10 to the minus 6. Leave the units alone. Okay. And in V is the source bandwidth in gigahertz. So there's no units either to that. Don't say gigahertz, just V. If it's 5 gigahertz, you just put a 5 there. Don't put 5 to the power of 9. It's wrong. Just put 5. So all these parameters, there's no units in it. Just put the number. Like 5 gigahertz, you just put a 5. If it's 100 megahertz, just put a 0.1 for V. Don't put a unit. Times 10 to the minus 3 or 6, don't put that. Guys, is that clear, this formula? This is for SBS scattering. It's only backwards, like I told you. In other words, the scattering goes back to the laser. The laser source injects light into the fiber, and the backward scattering goes back into the laser. And you know what's going to do this SBS Brulin scattering? It's going to bugger up the laser. It's going to damage the laser. It's going to try to make trouble and change the frequency. So it goes backwards, back to the laser where the light comes from. Okay? So the light is scattering in the fiber, but it goes back to the lasers. Remember, it's a backwards process only. Right. And it's non-linear. So if I ask you what it is, it's also non-linear. It says here somewhere, non-linear. Right. SRS scattering. There's a formula. Same formula, except this is a 5.9 now. Times 10 to the 2 times D is again D, that D value, which is just the value without parameters. Lambda without the units, and the diameter again without the units. And there's no V here. You see, this one doesn't have a V. It doesn't exist for this formula. So this is Raman scattering. And this is also, now this one is interesting. I've written in red here. Your books don't have this in. I've written it both forward and backwards. It says here in a text somewhere. This scattering is forward and backward. So the laser puts light into the fiber forward, and then some of that light scatters back into the laser, making trouble there. And this is Raman scattering, the one that goes forward and backwards. Okay. You must know this example, do this example. 3.3, there it is, both of them. People, I'm going to get load shedding just now. I'm just waiting for it, and then I will just save that file. Okay. Fiber bend and loss. This is fiber bending, and there's the formula for it. The radius of curvature, how much you bend a fiber. If you bend it 10 centimeters, then it will be 0.1 meters here. So there it is, 3 times N1 times lambda over 4 pi N1 minus N2. This is the minimum radius of curvature that you're allowed to bend that fiber. You can't bend it less than this. It will just break, and it will just scatter too much. It will not work. So the attenuation coefficient is this one here, alpha. It's attenuation efficient, but we don't use that coefficient here. We just calculate the radius of curvature here, and then we can calculate how much can we bend that fiber. But fiber bend losses actually occurs, it's evanescent. You see this evanescent word here? It's evanescent losses, and these evanescent losses will cause a lot of losses when you bend that fiber, and a lot of energy will escape. Now, they talk a lot of stuff here, and you can read here what is fiber bending losses. It's basically when you bend it and then there's evanescent losses. The minimum radius that you can curve it, that you can bend the fiber, there's your calculation. It's not in your data sheet. They will not tell you. You'll get this out of the data sheet. N1 and N2 is in the data sheet. But then you must calculate those curves yourself. Your boss will ask you one day, how much can we bend this fiber? And you say, don't know. The boss will also not know. So please, guys, learn this formula so you can show your boss how do we calculate the bending of this fiber around the corner. We want to maybe put it in ducting. We want to put it below a floor. We have to bend it. What's a minimum we can bend it? You use your data sheet. You get these numbers from it. Okay? Then you calculate the curvature, the maximum you can bend this fiber. You guys, you understand now what's bending of a fiber and the bending curvature. Also, there's a thing called micro bending and macro bending. When I talk about macro bending, you see this word here, macro bending. It means a big bending. You can see it with your eyes. People, micro bending, you can't see it with your eyes. It's smaller than a millimeter. It's smaller than a COVID virus. Micro bending, you can't even see it. But macro bending is the one you can calculate here. Macro bending is the one you bend it around the corner physically while you're laying your cables. Alright? The guys lay the cables under the street, they bend it. That's macro bending. Okay? Now, with macro bending, this is what happens. The core is there in the cladding. So it's stretching the cladding, you see? And you see this radiation. This is evanescent losses here. This radiation. That's your evanescent losses. Okay. Let me just get rid of this ugly thing. How do you get rid of this thing? There you are. Okay, so microbending. So how can we get it, reduce it? How can we remove it? Designing fibers with large curvature and index differences. Do you see here? Relative refractive index difference in 1 and in 2 is large. Then you can reduce microbending. Another way, operating at the shortest wavelength possible. Okay? And then also, don't bend it too much. Physically, don't bend it too much. 3 things. Okay. Now, there's a bit of a difference. The radius curvature for single mode fiber. Single mode fiber don't want to be bent. You remember that light must shine straight through it. You remember? Without bouncing. Single mode fibers, you can't bend it. It's a problem if you bend that one. If you have to go around the corner, you can't. Go straight. It's a problem, people. You don't bend it. But there is a radius curves bending, that's a minimum for it. Don't bend it less than this. This is the special formula for it, 3.9 market, you must know it. So for single mode fiber, it's got a different radius of curvature formula, okay? Right, two-step X fibers have got the following parameters. Estimate the critical radius of curvature, and so on. This is the calculation for that. Remember, there's a mistake in the book. This is not to a half there. It's a 3/2. I found this mistake in the book. And just so it's to the power 1.5 here. I've marked it in red here, that formula. So your own files, if you can download this book or you buy this book, just write in pencil. There's a small mistake in this example. Okay, go and calculate this, then you'll see. And they calculate the cutoff wavelength, and they do everything in the radius of curvature for single mode. You see it's 34 millimeter. It's much less than that one. What is that one? I didn't see what it was. But okay, 34 millimeter. You can't bend it less than that. Right. Mid-infrared and far-infrared transmission. The band is from here. I'm not going to talk much about this. I'm going to really skip this stuff. But I'm going to talk about dispersion, and this is some dispersion stuff here I've written in red. And the book is not so clear about it always. So sigma S is the RMS pulse broadening due to intermodal dispersion. Do you see there? Sigma M is the RMS pulse broadening due to material dispersion. This one is due to intermodal dispersion. This is to material dispersion. See the difference? Sigma lambda, the RMS spectral width of sigma S. The RMS spectral width of this one. Is that one. So sigma G, pulse broadening for graded index fibers. So it's very confusing. They talk about these sigma values throughout the text and it's a bit unclear. So sigma G is a pulse broadening per unit length. In other words, per kilometer. You see there. Pulse broadening is in picoseconds per kilometer. It's a time delay. So sigma G is like a time delay of say 5 picoseconds per kilometer. Sigma C is chromatic. That C stands for chromatic. Chromatic broadening. Okay. And sigma N is intermodal broadening. Okay. And sigma T is the total dispersion time. So dispersion gives us a delay. And that delay time we want to measure. And we're getting to that now. So dispersion is actually transmitted along the fiber and it causes distortion for us. You know what's distortion? We call it third harmonic or second harmonic distortions. It's distortion on our frequency. Say for instance we transmit 100 megahertz in it and we see there's a distortion at the third harmonic, which is 300 megahertz. So there will be some distortion at another frequency. So distortion causes other signals that we don't want. That's what it means. The magic word for that is dispersion in English. Dispersion is basically distortion. Now all these sigma things has to do with dispersion delays. And it actually causes a delay for us. It causes pulse broadening. That pulse broadening. Maybe I can just draw for you on the camera how that looks. Let me just put my camera quickly on. I'm going to stop this one. Guys, can you see my hand? Can you see my camera? You have to give me feedback. Can you see?
Yes, we can see it.
Okay. I'm going to input the pulse into the fiber like that. Square edges, square, square. Nice, ne? But after some pulse broadening, what will happen? This will happen. I'm only drawing the upper edge there, and this will happen. So maybe this is sigma S, that's due to sigma N, and this is due to sigma G. So I've got one color, 100 megahertz, and the color is, say, 100 nanometers, and say it's red. But here I've got three colors. So the dispersion caused us three different modes, and also it caused a widening here on this thing. A widening there. That widening is the total dispersion value. Now you see what it is. When it goes down there, I'm not drawing it nicely, it will go like that, and that one will go like that, and that one will go like that. And they will all three mix in. So there will be a very uncertain up edge. When you look at an oscilloscope, it will jitter like that. They call it jitter. It will jitter left and right like this. And that down edge will also jitter up and down. So you never know, is this the down edge or is that the down edge? How much your IC know when to switch? So TTL logic ICs, it's got a certain uncertainty. So this width here will be your total sigma. What did I say is the total sigma in? So the total. But in real life it can look like this. It can really mix in such ugly that you can't even figure out. It's very wide, it's very narrow there, it's very wide here. So much that your gap here for a 1 is only very narrow there. It almost disappears. And when the noise is becoming bigger, it totally disappears. So this is not a 1 anymore. You can't figure out what this is. So if it was a 1, 1, 1, you'll have, it will be like this. It will be so colored in that you don't know what is ones and zeros. That's a 1, 0, 1, 0. In there's now logic, the logic value, which you output at your output to your control board. Now that logic value, you can't discern anymore what's going on. This is due to dispersion. It's a delay from there to there, that delay. And it's jumping like my pen, it's jittering left and right all the time. Okay, you understand? Now better. I'm going back to my notes. Oh, no, I must find the notes now. Okay. So the broadening that I'm talking about here, this broadening, the pulse broadening that one I've drawn on the picture now for you, the pulse broadening time, it's called the digital bit rate, and the maximum bit rate is in this case BT. Now tau is the pulse broadening. Also tau is the input pulse duration. So that pulse that I've drawn you there, this is actually the time. And that time determines the maximum bit rate. So if the dispersion is too much, this bit rate will be limited by that. So your bit rate will be limited by a dispersion problem. So we need to calculate when will this fiber stop working. And at this point, in the red here, we have set the maximum digital bit rate. This is where that thing is still clear. You can see it's a logic 1. The moment it gets total blackened out, then it's not a 1 or a 0 anymore. That is when the fiber stops working. To make it work again, you've got to lower your frequency, but you can't go high enough for that fiber. This is a problem nowadays because they want to put more and more cell phones. Vodacom want to put more and more cell phones on the same box, and it's just going past its bandwidth. It just can't do it anymore. And they're adding cell phones, and that's why you'll end up with cross lines in cell phones that go click and cracking, and your voice is breaking up, and you can't hear your mother, and you can't hear your boyfriend. That's so sad. That's not very nice. It's all due to this problem. So we are at the problem which we experience daily with our cell phones this one year. So I'm just gonna, you guys must really read this paragraph, okay? Between formula 3.1 and formula 3.11. You must know these formulas, and you must know how to calculate the maximum bit rate. So remember sigma in this case, sigma is the RMS output pulse width. The output pulse width, it can be in nanoseconds, whatever. So sigma is that pulse width in microseconds or nanoseconds. Or it's a RMS pulse broadening. And it's 0.2 over sigma, and that will be your maximum port rate. And also, it's the same formula, 1 over 2 tau. Tau, in this case, tau is the delay. It's your pulse broadening time there. That's where tau comes from. That's a very simple formula. It's not complicated. And I just show you here. There's a 10111. That's what I've drawn you now in the picture. And when this 1 and 1, we can still discern the two. But as the pulse broadens here, they're mixing into each other here, né? You see. And when they're mixing into other, they start making trouble. And here you can see the big trouble. They're mixing the pulse broadening even more here. And now you can't see it's a 0, 1. You can see that's a 1. You can see that is a 1. But you can't see what this is. There's a 0 here. And there's a 1. So it's 1, 1, 1, 1. It was 1, 0, 1, 1. You see? So you can't see if that's a 0 or a 1 anymore. Because of this broadening. Sigma is this broadening from this beautiful one to this bad one here. Okay. Now your bandwidth, people, it's slightly different than a max bit rate. You see that's a max bit rate, but your bandwidth in frequency, your bandwidth is 2 times B. So your bit rate is 2 times bandwidth. Okay? Just a simple formula that tells you how to go from bit rate to bandwidth. Bandwidth is a frequency, and it's usually cut into half. You guys can read here why, and so on. I don't have time. Look, we don't have load shedding, eh? I've passed that point. Looks like we are lucky. Guys, then you must know this drawing 3.9. You can mark it. It's yellow. You must know it. This is, if I ask you a question, I ask you, give me the difference between multi-mode, graded index, and single mode fiber. This is the difference. This one is a step. You can see the step there in the N1 and N2 core. The input pulse there is so narrow. Okay? The meridional rays will transmit like this. You see there. And the output spread, the maximum bit rate or the bandwidth will look like this. Low amplitude but very wide. You see. The time delay from there to there, tau from there to there is very wide. So it's very much dispersed. You see the dispersion there. This one is less dispersed because the pulse width is narrower. The input pulse width is this, and the output pulse width is better than that one. And for single mode fiber, it's even narrower. It's as narrow as in the beginning. But the meridional ray goes through the axis here, straight. Pambile. They say, Hamba Pambile sê die Zulu, né? So it means it's going straight through the fiber. It don't zigzag like this. This one is giga, giga, giga. Yeah, but giga. When you drink a bit much, that's what happens. This one travels also I almost said giga, sorry. Skip I almost skip to English, ne? So straight. This is round. It's making the path longer. This one, it's just straight. So this is your single mode step-in X fiber. This is your multi-mode fiber. And that is your multi-mode step-in X fiber. But this is graded, sorry. The word missing here, multi-mode, is actually wrong. It's graded index fiber, okay? Will you change that? I must actually write it here, graded. So multi-mode step-in X, multi-mode graded index fiber, and multi-mode single mode step-in X fiber. This drawing is worth in exam 10% of your year mark. 10%. Because one mark there, one there, one there, one mark there, and there. You see, one mark there, and there. At least 10 marks for this picture. So you must know it, okay? I'm glad we're going to make it because I was worried about this load shedding. Sorry, now you're going to have a longer class. Now, this example, go through it, people. I don't have time. But look at the way they ask it. It's a multi-mode. It's got a pulse broadening of 0.1 microsecond and it's over 15 kilometers. Now calculate the pulse broadening. So first calculate the bandwidth, the optical bandwidth. So your bandwidth is here. It's that formula I showed you, and it's 5 megahertz. That's your bandwidth. Okay. Your dispersion is like 1 over the bandwidth. It's in time. So it is that one over 15. Because it's a 15 kilometer distance, ne? It's a 15 kilometers. So dispersion over 15 kilometer distance will be 6.6 nanoseconds per kilometer. You see. If it was 100 kilometers, it will be like 1 nanoseconds per kilometer. So the bigger you make this, the less the dispersion becomes. So dispersion is measured in time. Bandwidth is measured in megahertz, in frequency. That's the difference between them. Learn that. Okay. And the bandwidth length here, give me the bandwidth length, then it's the 75 megawatts kilometer. This is called your bandwidth length. There it is, you see? Bandwidth length. Please go through this example in your own time. Chromatic dispersion. Now we're getting to those sigma C that I talked up there. I talked about it up there. So TG is your group delay. Remember I said it's a delay, dispersion emitted in nanosecond. So the group delay is this. But the formula that you must learn is actually this one. TG is 1 over VG. Okay? So that's your group delay. And that's your group velocity. Remember I said we carry on page 161 earlier this morning. And this is this page where we talk about this group delay. There was another formula there. On formula 2.37. In formula 2.4. Remember those two? Look at those two in relation with this VG. And then you'll see this formula is used there as well. But now you understand it better. Because you've got the background info. What is this time delay? It's to calculate the total dispersion. So sigma m is this one, and it's due to pulse broadening due to dispersion. This one. RMS pulse broadening due to dispersion. So use this formula, and then what else? And then this one. So Your material dispersion is due to the material in the fiber, and this is sigma m is sigma lambda over L over C. Okay, C is the speed of light, so speed of light, you must know what's the speed of light, guys. We've done it in matric.